In this video, we're going to talk about the heat changes during a chemical reactions. All right. And so, one important term that we need to talk about is bond dissociation energy. Now, dissociation energy is the amount of energy that must be supplied to break a bond and separate the atoms in an isolated gaseous molecules. All right, so what does that mean? Well, basically, the strength of a covalent bond is measured by the amount of energy that must be supplied to break it. So, the greater the bond dissociation energy, the more stable the chemical bond. And the more stable a molecule, more stable the chemical bond, then the less reactive it is. All right, so let me show you what does that mean. So the figure that you see here are just the average bond dissociation energies between different atoms. All right, and so the numbers that you see is basically how much energy it takes to break those bonds. Okay, and then on the flip side is how much energy is released if those bonds were formed. All right, so it could kind of go either way. And that's just due to the law of conservation of energy. All right, so the law of conservation of energy basically states that energy cannot be created or destroyed in any physical or chemical change. All right, and so when you're thinking about these bonds, the amount of energy it takes to create those bonds is also the amount of energy it takes to break those bonds. Okay, now a couple of things I want to pull your attention to. Is that typically the more bonds you have, the greater, the more stable it is. Okay, so for example, if we look at this CC bond, right? So this bond represents it's a single bond between these two carbon atoms. Okay, and so like for example, if you think about like ethane, right? Ethane is two carbons, all right, bonded together, and then you have these hydrogens. So essentially, we're looking at this bond here. How much energy does it take to break the single bond between these two carbons? Okay, and then we see that it takes about 410 kilojoules per mole. So if you had a mole of the substance, it takes about, I said 410, I'm sorry, it takes about 350 kilojoules of energy to break that bond. All right, but now look at the multiple bond. If it turns out you have a double bond between the carbons, so something like a compound like this, ethylene, right, versus ethylene, then what you're gonna have is that it takes about 611 kilojoules of energy per mole to break that bond. Okay, versus if you were to have like a triple bond. All right, so something that looks a lot like this. So C2H4 or C2H2, I'm sorry, versus C2H4 versus C2H, this is H6. All right, the amount of energy it takes to break the bonds between these two carbons is 835 kilojoules per mole. So what does that tell us? Well, it tells us that because it's a greater amount of bond dissociation energy, that if you have a triple bond, this bond is more stable than if you have a double bond versus if you have a single bond. Okay, now the more stable it is, the less reactive it is. So we could rightly say then that this molecule is probably most likely less reactive than something like C2H6. All right, in which honestly that is really the case. So now, and we kind of talked about this in the previous video, that when you're making bonds, all right, this process is exothermic. That means it's releasing energy. And if you're breaking bonds, this process is endothermic, and so you need energy. And so, like for example, let's just kind of use hydrogen as an example here, where the HH bond, the bond dissociation energy is 436 kilojoules per mole. All right, and so I'm kind of erase this here. So for example, if you were to take two hydrogens, right, and it creates a bond, right, it's going to release 436 kilojoules of energy. And the way that we show this is that we put this on the product side. So when we put this on the product side, it shows that it's a product. All right, it's releasing. It's as I said, it's a product. Okay, versus if you were looking at the opposite direction, where you have this bond and you were to break the bond between these two hydrogens, and these dots here just represent its one valence electrons. All right, what we see here that we're going to require 436 kilojoules per mole of energy. And so when you're requiring that much, or if it's an input, we put that as a reactant because we need this energy for the reaction to take place. Okay, now remember this here, it's an exothermic. All right, all exothermic reactions energy or heat is released as a product. And all endothermic reactions, all right, energy or heat is a reactant. So you need it in order for the reaction to take place. So in every chemical reaction, we either have, there are some bonds in the reactants that are broken. Some bonds are formed in the product side. And we often like to try to figure out how much energy is associated with that chemical reaction. All right. And so the change of the energy that's associated with the chemical reaction, we simply call the heat of reaction. All right. Now, the heat of the reaction, once again, is basically looking at the difference between, let me just go ahead and write this out. So if we're looking at the difference between the heat energy absorbed in breaking bonds and the heat energy released in forming bonds. Okay, and so that's what we're kind of looking at here. And so when we're talking about the heat of reaction, we're looking at the difference between, okay, how much energy was needed to break all the bonds from the reactants, and how much energy was released when we're forming bonds in the product side. Now, when we see that in most cases, there is a difference between what's going on the reactant side versus the product side. All right. And then we get to measure what we call the heat of reaction. In all the other words of the heat of reaction, we tend to call this enthalpy. All right. Or the change of enthalpy, which is notated as a delta H. Okay. Now, this value, delta H, represents, as I said, the enthalpy change, which occurs during the reaction. Or, other words, what we're looking at is the energy difference during the reaction. All right, and so sometimes you see it's as heat of reactions. Other times they call this as delta H, or the change of enthalpy. All right, so we just make sure that you understand that these terms are usually interchangeable.